Let's talk a little bit about misfire detection strategies. Now, what you're going to see on this vehicle is a random misfire that shifts randomly from cylinder to cylinder. So we're going to prove to you that if you take some time and make some measurements on this vehicle, you're going to save yourself a lot of diagnostic work. This happens to be an internal coil type system, so we can't gain access to secondary. So what we're going to do is backprobe primary, and you'll be looking at a primary waveform on your scope screen, and what you'll witness on this vehicle is a misfire, again, that randomly shifts from cylinder to cylinder. So let's go ahead and look at this misfire, and watch very carefully, because you will see the misfire does not affect just one particular cylinder. It'll shift across that scope screen. You see it here, and you see it here. Now, looking at this primary waveform, and remember we said measuring the values is critical. You will notice the lab scope is set at 50 volts per division, so you will notice the primary inductive kick is good at about 300 volts. If you focus on the spark duration period, we've got a good, healthy 1.5 millisecond spark duration period. That tells us that the secondary loading effect is good. This misfire cannot be caused by anything in the secondary circuit. Okay, let's take a look at this DREV triggered signal from the crankshaft position sensor. If you watch closely enough, you will see the loss of the signal, which obviously created the loss of a primary function. Now, the secret here is to give your scope a lot of time, in other words, a lot of toggles. The more toggles you have on that screen, the better chance of seeing the glitch. Now, if I increase my time base and show you more toggles on the screen, you can see that the glitches show up more frequently. The mistake a lot of technicians make is they may show only 1 or 2 toggles on that screen, and you have minimized your chances of seeing a glitch with just, let's say, 2 or 3 toggles on that screen. So in the event that you're looking for glitches, give your scope more time with a whole bunch of toggles, which will increase your chances of seeing that signal dropout. We're faced with a no spark, no start situation on this Toyota. Now, most of you technicians know Toyota igniters are not cheap, nor are the coils. So before we replace any components on this vehicle, let's dynamically test the most important signal in the car, which is the pickup coil. Now, the ohmic value that Toyota gives you on this vehicle is about 130 to 160 ohms. We have ohmed out the pickup coil. Ohmic-wise, the pickup coil checks good. Now, to dynamically test it, what we've done is we've taken the lab scope, and during cranking, as in most pickup coils, but not all, but in most pickup coils, during cranking, we want to see a peak-to-peak voltage of 1 volt. Okay, we set the scope at 500 millivolts per division, half of a volt. We cranked the core over. Now, because of the cranking RPM being relatively slow, what we've done on the time base, we've gone to 100 milliseconds per division. Now, what you're looking at on the scope screen, remember, if you reference your ground tick mark, the voltage that goes above ground is a positive slope, and a voltage that goes below ground is a negative slope. A peak-to-peak voltage would require us to add the positive slope and a negative slope together. Remember, we wanted a minimum peak-to-peak voltage of 1 volt. As you can see, we're short of that, so we're suspecting a weak pickup coil. You can see the ohmic check of this pickup coil shows it to be perfectly good. But remember the limitations of a digital ohmmeter. We're only applying 0.5 volts into the circuitry of the pickup coil, and a spec for Toyota gives us, we're right in the middle of that spec. So remember, ohmic check of pickup coils do not pinpoint weak magnets or too much of an air gap, so just because it passes the ohmmeter test does not mean the pickup coil is good. If you recall, we dynamically tested with a lab scope to prove to you that peak-to-peak voltage was less than 1 volt. Now, before we go to replace any components on this Toyota, knowing the expensive coils and igniters, what we're going to do, we suspect because of the weak pickup coil signal on the lab scope that we do in fact have a weak pickup. But we want to show you a way that you can trigger the igniter yourself with a plain Jane cheap soldering gun. So let's go ahead and go to the vehicle and show you how easy it is to trigger the igniter to make certain the igniter is working properly. Now, in this no spark, no start Toyota, we know the pickup coil is bad because if you recall, the peak-to-peak voltage was less than 1 volt. So we want to make sure that the igniter in the coil is good. So what we could actually do is take a soldering gun. We pull this trigger close to the igniter, and a magnetic field off this soldering gun will bias the igniter if it is good and fire the coil if it's good. So let's go ahead and do that. If you focus on the spark tester, if I get that soldering iron very close to the igniter, notice the spark tester. So we know the coil and igniter is good. Okay, there's another way you can do it if you don't have a soldering gun. I could take one finger and go to the positive battery terminal, pick up some battery voltage, I can take my other finger and I can bias the igniter with my body through the battery terminal. Okay, let's look at a primary parade pattern. And what we're doing here obviously is back probing primary coil negative terminal. And we will prove to you that, remember, that any secondary misfire will be in fact mirrored in the primary pattern. So if you look at a screen right now, you'll notice that at 100 volts per division, notice that we're looking at about a 350, 375 volt primary inductive kick. You'll notice that all 6 cylinders are uniform on the inductive kick, or what some people call the firing line voltage. At any rate, we know that the secondary loading effect is uniform between all cylinders, and just like a parade secondary pattern, a parade primary pattern only gives us the benefit of looking at a voltage value. The spark lines are too compressed to make any kind of diagnostic decisions. So with that in mind, what we have to do is we actually need to go to a primary raster pattern and focus on a dwell period, maybe trying to pick up a dwell variation problem to see if maybe we have too much slop in the distributor drive gear, distributor bushings, timing chains, etc. This is the pattern that you need to use in the event that you have any kind of erratic dwell variation problems. Before we make any kind of diagnostic decisions, we need to go to that dwell section of that primary waveform to look for uniformity. Well, as we talked about earlier, remember the point of primary turn-on is when we begin the charge process of the coil. What we're looking at here is uniformity, comparing the uniformity between the points of primary turn-on. I will tell you this, because of the dwell circuitry that is built into the modules, whether it's a Ford TFI4 or an HEI system or a Toyota TCCS systems, what you have to understand, the modules and the igniters, when you force that system back into base timing, the modules and igniters do in fact have some dwell increase capability built into the module. For example, a GM system will advance at 9 to 13 degrees as RPM increases. Now if you look here, you will notice that the scope is on 1 millisecond per division, and you can see even though there's a slight stagger here, this is perfectly normal. We will tell you that when you're looking at the alignment, is that if you see more than 1/2 of 1 millisecond variances, that would be indicative of maybe too much mechanical wear in the distributor shaft, too much mechanical wear on the distributor drive gear, a sloppy timing chain, a magnetized distributor shaft, magnetized shutter blades on Ford's TFI4 systems, things like that, upper distributor shaft bushings like on the Honda systems, etc. So give it the maximum 500 microseconds or 1/2 of 1 millisecond variation is perfectly normal. When you have the mechanical slop or the magnetized distributor shaft or shutter blades or whatever, you will see an abrupt, massive misalignment of the point of primary turn-on on this raster pattern, indicating that you have a primary dwell variation problem. Okay, let's look at a problem vehicle that came into my shop, believe it or not, towed in with a dead fuel pump. Well, this vehicle had 60-some thousand miles on it. We put the fuel pump in the vehicle, got the vehicle running. We took the 5 minutes to scope the car. And we're talking about a maximum 5 minutes. Well, what do you see on this pattern? If you'll notice the scope is set at 5 kV per division. This is a 4.3 with a 45,000 spark plug air gap. Now, at 5 kV per division, you will see that the secondary kV demand is in excess of 20,000 volts. Now, if we hadn't caught this, you're going to be assured down the road that we would have had a severe ignition failure sooner or later. Well, since the kV values went so high, let's see what effect it had on the spark duration. Keep in mind that we want to see a minimum 1.3 millisecond spark duration on any DI type system. Well, on this particular vehicle, we have superimposed secondary, and notice our spark duration period at 1 millisecond time base on our scope measures below 1 millisecond. Yes, the car ran. At that point, no, there were no symptoms. But remember, the leading cause of internal coil carbon tracking is what? Excessively high secondary firing KVs. So let's go ahead and investigate what caused all 6-cylinder firing KVs to be too high. It's got to be one common denominator. There it is. Now, if you take the ohmmeter, this is a little bit tricky, so we will tell you that when we ohmed out that high voltage tower, the carbon button, inside the distributor cap to the coil wire terminal, that the ohmmeter, when the cap is still at operating temperature, ohmed out as an open circuit. So we know we got a bad cap. Now, if you let that cap set for 10-15 minutes and let it cool off, the ohmmeter ohms that cap out as perfect. In other words, 0.3, 0.5 ohms. So we're basically telling you that when you took your scope and scoped that car under normal operating temperatures under dynamic conditions, then and then only would you have seen those excessively high firing kVs to alert you to a problem that's common to all the 6 cylinders. Okay, let's go to a problem vehicle and do a scope check, and let's see what the ignition scope is trying to tell us on this vehicle. We want to prove to you how important it is to scope check a secondary circuit in the event the car comes in a tune-up with some mileage on it. In other words, we're looking at a high mileage vehicle that's a little bit rough, choppy idle. Car came in for a tune-up. You're looking at a parade pattern on the secondary right now. You will notice that you're firing roughly about 10 kV. Now what I'd like to do here before we get out of this parade pattern, I would like to do a wide open throttle snap, and what you're going to witness is the firing voltages are all going to go real high, verifying that compression is good and the volumetric efficiency of the engine is good. So let's give it a wide open throttle snap. You'll notice our firing voltages actually exceeded the screen. In other words, they went to 16, 18 kV. That basically tells us that compression is good. Now, mechanical integrity of the engine has been pretty much verified. So what I'd like to do right now is go to a single cylinder one at a time, and let's focus on the spark lines. Now remember, what we're doing is a 5-minute scope check. We're looking at secondary kV values on the parade pattern, and then we want to focus on spark line characteristics of all the 6 cylinders on this vehicle. So let's go to a single cylinder, and let's look at each cylinder one at a time. Now that we've gone to a single cylinder pattern, if you remember during our DI presentation, we said a distributor ignition system spark duration period at idle, in park, no load, should never dip below 1.3. Well, what you're witnessing here on a 1 millisecond time base, looking at cylinder number 1, you can see that we are barely maintaining a 1.3 millisecond burn time. Well, let's go to cylinder number 4 right through the firing order. Let's bring number 4 up here, and let's analyze the spark line. You can see that it is maintaining about a 1.2, maybe a little bit higher spark duration. It's a little bit longer than cylinder number 1 was. Let's move on to cylinder number 2. We bring up number 2, and you can see it's showing us a problem. Notice that the spark duration period is barely 1 millisecond. Obviously, that's well below the 1.3 minimum that we're requiring. As you can see also, when you look at the spark line is in fact bending upward, indicating a lean condition inside that cylinder. Now, this is a case where the car is in park, no load. If we would bring this car and drive and power brake it, you would see the angle even bend abruptly upward more. But let's go ahead and look at all the 6 cylinders here. You're now looking at cylinder number 5. It's pretty much showing you the same thing as number 2 cylinder. The spark line is bending upward. It's shorter than normal, verifying the fact that we have another lean cylinder. Let's go to cylinder number 3. Looking at cylinder number 3 spark duration, it's a little bit better. As you can see, it's hanging at about 1.2. Let's go on to cylinder number 6. Looking at number 6, it's a halfway decent cylinder too. So what you basically looked at on this 6-cylinder engine is 3 cylinders have a spark duration period well below the 1.3. So what we're going to do on this system before we make a diagnostic decision to tune the vehicle up, we want to go to the primary side of the circuit and focus on the dwell section to make certain that we do not have any dwell variation. Now, if you remember, we saw some relatively short spark duration periods in secondary, which alerts us to a problem. Before we make a diagnostic decision to tune this vehicle up, we want to go to the primary side of the circuit to make sure we do not have any dwell variation problem. Now, what you're looking at here, focusing on the point of primary turn on in the primary dwell section, you will notice the alignment. As you recall, on the DI presentation, we told you that they will never be perfectly lined up, and the maximum variances that you should see when comparing cylinder to cylinder is a maximum 500 microseconds, which is typically 1/2 of 1 millisecond. You can see we have that. But let's bring it off idle up to about 1,000 RPM and make sure that we don't have any massive dwell variation problems. As you can see, I've frozen the pattern. And again, the scope is on a 1 millisecond time base. You will see slight variation problems because as the RPM increases, we will turn on primary sooner to ensure that the coil got sufficient coil charge time. As you can see, we still have a little bit of misalignment here. This is not a problem. At 1 millisecond per division, you can see that we still are within no more than 500 microseconds variation between the points of primary turn on. So don't make any kind of diagnostic decisions because the points of primary turn-on are not perfectly lined up. We will give you, again, a maximum of 500 microseconds variance. So hopefully we prove to you technicians that this scope check is a 5 or 10 minute job max. So what we basically did, we've done a tune-up verification procedure. We have qualified this car for maintenance tune-up. So what we're going to do is we're going to do the intake cleaning that we talked about, the injector cleaning, and of course R&R, the secondary components. So we'll bring the car back in there after we do these maintenance procedures and show you the improvement on the spark duration period, obviously, which would improve the drivability of this vehicle. Well, let's look at a raster pattern after the tune-up, and let's see how much better our spark duration periods are now. You can see the scope is at a 1 millisecond time base, and if you recall, 2 of the 3 cylinders were below 1.3 millisecond spark duration. Now after the tune-up, you can see all the spark duration periods are in excess of 1.3 milliseconds. Okay, let's talk about the EI systems. Now remember, EI is the new term for DIS. So when we talk about EI systems, we have to ask ourselves, just like we did on DI, how many air gaps, authorized air gaps, are there in an EI system? The answer would be 2. Remember, we are firing 2 spark plugs simultaneously. The reason why we're saying that is if you have an unauthorized air gap in one side of an EI or DIS type system, it's going to affect the spark duration of both 1 and 4, let's say companion cylinders. So with that in mind, it's going to be real critical just on EI as it was on DI to look at your minimum spark duration values. Now, I know we said this before, but remember, General Motors Type 2 DIS coil packs on their EI systems will only maintain a minimum spark duration of 1 to 1.2 milliseconds. So that we will tell you on those systems, if you see a spark duration below 1 milliseconds, there is something wrong with the system. Now, most technicians will use a spark tester, especially on EI type systems. But what you have to understand is you're looking at 3 different flavors or 3 different types of spark testers. The spark tester lower left-hand corner is what we call the true ST125, meaning that it requires 25,000 volts to fire that. If you were into checking the vertical calibration of your scope, a good idea would be to use a true ST125 spark tester to check that. Now, if you're going to do that, you have to make sure that when you inductively couple your secondary kV probe to check the calibration of your scope, you have to be on a negative firing event. You want the kV probe before the air gap across the spark tester in relationship to current flow. So you have to be on a negative firing event. If you are on a positive firing event, your kV probe is downstream of the air gap, and your kV probe picks up the voltage potential after the voltage drop across that air gap of that spark tester. The kV spark tester on your right is what we call low energy. There is a need for those. For example, for those technicians that will take 2 of the ST125 spark testers to double stress a GM Type 1 and Type 2 coil pack, that's great. If you take 2 ST125s and clamp them together, obviously that's a kV value of 50,000 volts. The GM Type 1 and Type 2 coil packs have the kV potential to easily fire 2 ST125s clamped together. However, on a Chrysler DIS system, that Chrysler coil pack doesn't pack the kV potential to fire 2 of the ST125s clamped together. So if you look on the right, this is what we call a low energy spark tester. You can see the center electrode protrudes out a little bit, and this spark tester requires 15 kV. So for those of you who like double stressing coil packs on Chryslers, you want to make sure that you do not use 2 ST125s rather than use 2 of the low energy clamped together. That gives you a kV demand of 30 kV, which the Chrysler DIS coil packs have the ability to do that. Now on Ford multi-spark systems, beginning in 1990 on the 1.9 Ford Escorts, where we fire that spark plug 4 times, it will not like a dual ST125 spark test. Okay, so that system will bail out. If it is a 94 or later multi-spark Ford, they still will not like double stressing a coil pack with 2 ST125s. Our recommendation to you, if you want to stress a coil pack on a Ford or a Chrysler, use the 2 low energy clamped together. Now remember, spark testers have severe limitations. If you have a misfire and you take a spark tester, if that misfire is electrically related, then your spark tester will show it to you. But if your misfire is lean density type misfires, rich density type misfires, or density type misfires, or worse yet, a mechanical compression problem, you're wasting your time as spark testers. That's why we said time and time again, the best thing you can do is just take the time, hook the scope up, read the firing times under dynamic loaded conditions on that vehicle, and make your diagnostic decisions based on KV demand, spark KV point, and spark duration periods. Okay, on a DIS circuit, which is again is now called EI, remember this is a simple series circuit. We said earlier that a DIS circuit has two authorized air gaps, in this case the spark plug air gaps. Remember, if we make this coil pack 1 and 4, when you have a 1 and 4 firing event, one cylinder is on the compression stroke, the other cylinder is on the exhaust stroke, which is what we call the waste firing event. What we were going to tell you here, if by chance you have a poor terminal connection at the plug or at the coil pack on, let's say, number 4 cylinder, or worse yet, an open from a hot spot inside that secondary lead on cylinder number 4, it's also going to affect the spark duration period that you're going to see on cylinder number 1. So let's suppose that we have an air gap in a plug wire, again here on number 4. If we put a lap scope on number 1, and let's make this a GM type 2, we want to see a minimum 1 millisecond burn time. Let's say we only show about 0.6 milliseconds. We know that there's a problem. Does that mean the problem is in number 1 plug wire? Well, no. Remember, it's a simple series circuit. If number 4 plug wire is open, it's going to create a lower spark duration period in number 1. So what we would do, if we take a jumper lead and go to the number 4 high voltage tower of the coil wire and slam it to ground with the jumper lead, which is bypassing the number 4 plug lead, and now you start to car up, and now you got a real fat 1.8, 1.9 millisecond burn time on a number 1 firing event. What does it tell us? The opening existed over here in a number 4 plug wire. You would have to do the exact opposite if your open is over here on the number 1 plug wire. It just, it's just a case in point that any open on either side of that circuit will reduce the spark duration periods of both cylinders. Now, for diagnostic purposes, it's going to be important for you technicians to always separate the KV demand for the true firing event that happens on a compression stroke and analyze the waste firing KV values, as you will see, because if you have an open in any of the plug wires, the waste firing KV value, if it is between 2 and 4 kV, that tells you electrically the plug wires are sound, and of course the terminal connections. And we'll show you that a little bit later on. Okay, let's go to an EI system parade pattern. As you can see, we use the old term DIS, but remember, again, the new term is EI. In other words, no more caps and rotors. So what you're looking at here is a parade pattern. Now, if you recall back on the distributor ignition type systems, when we looked at a parade pattern, we typically wanted to see uniform firing KVs when compared from cylinder to cylinder. Well, the uniformity that you saw back on DI type systems, you will not see on EI. If you look at my screen here, you can see that number 4 cylinder and number 2 cylinder, the KV demand is considerably higher than it is on 1 and 3. That's perfectly normal. That does not mean that the fixed resistance is bad on any of those cylinders. The reason why half the cylinders on a EI system will show a higher KV demand than the other half is because half of them are fired negatively, the other half are fired positively. So if we focus here on my left arm, if my armpit is a high voltage tower of the coil and it's a negative firing event, current flows this way. If my spark plug air gap is right here by my fingertips, if my KV probe is here, I pick up the voltage potential of that firing event before the voltage drop across the spark plug air gap. That's why you're seeing a higher KV demand on negative firing events, which is number 4 and number 2. Well, number 1 and number 3, we can tell you right off the bat, is a positive firing event. So looking at my other hand, when this spark plug fires backwards, my KV probe is here and current flows this way. That means that our KV probe is picking up the voltage potential of the firing event after the voltage drop across the spark plug air gap. It really makes no difference. The only reason why we tell you this is you're not going to have that 20% uniformity on KV values when comparing cylinder to cylinder. Now, your ace in the hole is just like it was back on DI type systems. Analyze the spark line. Any kind of problem in the secondary circuit, air-fuel ratio, fixed resistance problem is going to affect the spark duration period. If we have an open plug wire or a bad terminal connection, the easiest way to find that on a DI-S type system, here again an EI type system, is to look at the kV potential needed to fire the spark plugs on the waste firing event. If you look at our example here, the bottom traces are the waste firing events. In other words, left to right, there's your number 4 waste, there's your number 2 waste, there's your number 1 waste, and there's your number 3 waste. We will tell you that waste firing kVs should always be between 2 and 4 kV. Now, if you got an open plug wire, a bad terminal connection at the coil pack or at the plug, you will not be between 2 and 4 kV. So what we've basically done, and one of the nice things about the 5100 is we tell the 5100 we want to look at the waste kV demand. In other words, it allows us to pull up the waste firing events. As you look here on the screen, you will see that we are at 5 kV per division. And you can easily see that the waste firing kVs are between 2 and 4 kV. Now remember, we don't want to see a waste firing event go below 2 kV, nor do we want to see it go above 4 kV. As you can see, we're right where we should be. Now, that example here is the fact that if you look at the number 4 waste firing event, you can see if you use a 2 to 4 kV value, you can see that number 4 waste is in excess of 5 kV. That is telling you that you have an open plug wire. Now, let's get graphical here for you. If my left arm is that number 4 plug wire, and let's pretend I have an open circuit from a hot spot inside its secondary lead, and it's now blown open. You can't see it. Obviously, an ohmmeter may show it to you, but physically, visually, you could not see that without a scope. Well, if my kV probe is before the break and current flows this way, let's say for a negative firing event, my kV probe is before the air gap, the unauthorized air gap inside the secondary lead, then my kV value is higher than normal, and it's indicated by that 5 kV demand to fire that number 4 waste cylinder. Remember, we're firing these spark plugs with the exhaust valve open. There is no compression, so the kV demand should always be somewhere between 2 and 4 kV. Now, you can see number 2 waste, number 1 waste, number 3 waste look perfectly normal. If you're checking the electrical integrity of the secondary leads and the terminal connections on a DIS, EI type system, make sure you look at a 2 to 4 kV demand for your waste firing events. That tells you no other opens exist in those circuits. We've got a GM 3.8 in here with a rough idle. We have no idea what the problem is. We did, in fact, look at a parade pattern, and everything looked normal. So, as you can see on the scope, we have shifted to the raster pattern so that we can focus on the spark line. What I want you to do is focus on all the spark lines, but in particular, I want you to kind of focus on cylinder number 3, which is actually the second one from the top. Notice that cylinder number 3 spark line seems to be slightly shorter than the rest of them. Now, if you recall during the presentation, we told you a GM Type 2 coil pack will maintain a typically 1 to 1.2 millisecond burn time. The scope is right now set on a 1 millisecond per division. However, if you focus on number 3 cylinder spark line, you can see it consistently dips below the 1 millisecond burn time. We are suspecting a lean hole from an injector that's stuck shut. One of the problems with these Multec injectors is that they do intermittently stick shut. This is a classic example of a car that needs injector cleaning. But at any rate, to show you that number 3 cylinder spark line under dynamic loaded conditions, let's go ahead and put the car in drive and power brake it and watch what happens in cylinder number 3 spark line. Now you can see cylinder number 3 spark line is bending abruptly upward with a very, very high blowout point indicating a lean cylinder. Okay, what we're going to do here is a cranking kV test on this DIS 3800 system, and we want to prove to you that the kV bar graph and the kV demand is directly proportional to compression. After you see this good reading on the scope, what we will do, we will create a compression problem, and we will show you that a cranking kV test will in fact pinpoint the exact cylinder with the compression problem. If you look at the scope screen right now, you can see our kVs during cranking went roughly about 28 to 30,000 volts. Now remember we said the value of the cranking kV test is you're stressing the coil packs, you're stressing secondary insulation, and you just done an electronic compression test. Now if you look at the bar graph here, again because this is a DIS system, you will see the stagger between the kV demand comparing a negative fired cylinder with a positive. The negative fired cylinders will always be higher than the positive fired cylinders because of your relationship of your kV probe to the air gap and current flow. At any rate, you can see we're between 22 and 30 kV. So it's a good test to check the electrical integrity of the coil pack, the electrical integrity of the secondary insulation, and of course the compression of the engine. Now what we're going to do in this vehicle, we're going to create a compression problem. And we're going to show you how easily this scope picks up during the cranking kV test the cylinder with the low compression. In this example of a cranking kV test, we've actually created a no compression problem on one cylinder. Now let me run by you a formula here. The law of ionization tells us that it takes 80 volts of electrical energy to force current flow across a 1,000th inch air gap. So if we have no compression, like in this example with a 45 thousandths gap plug, you can do the math. It'll tell us that under zero compression, in other words, atmospheric air, it will take roughly about 3,000 to 3,500 volts to overcome that 45 thousandths inch air gap. So if you look at cylinder number 3 here, you can see the minimum kV during this cranking with no compression on cylinder number 3 did in fact tell us that it only took 3 kV, meaning zero compression, in other words 15 psi of atmospheric air. The easiest way to determine if a cylinder is low on compression is by doing a wide open throttle cranking kV test. Now obviously we're not telling you technicians to replace your compression gauge. We're telling you that in cases like this where you have one dead cylinder, in this case, number 3 cylinder would be the guy that you would want to back up and verify with your mechanical compression gauge that in fact this is a problem.